Welcome back to ECE 220. Second day, day 2. Your passport assignment, several of you have turned that in. About 20 more have turned that in already. That's a good sign. You're actually able to access the material. Homework number 0. Several of you have started that, and some of you have already completed that. That's due Saturday. And after class last time, someone woke me up and said, I didn't see any lab points on your grade distribution. And I said, I knew I was forgetting something. Duh. So the lab is worth 20% of your grade, and here's the kicker. You have to turn everything in, even if it's late and you're going to get 0 points for it. I'm using the Dr. Marsland strategy. So he's learned that you need to turn in everything, whether you get credit for it or not. Yes? That doesn't add up to 100%. Very good. What that does add up to is 115%, and I'm going to eliminate your lowest midterm grade. You have 4 of those, so one of those gets removed. That gets us back to 100%. Does that make sense now? Yeah, I looked at that and I go, let's see, am I adding right? Oh, yes. Somewhere here, maybe not readable on this amount of information, but I tried to make it, you couldn't see that until I scrolled down, but the lowest midterm exam score will be dropped. The late policy is pretty strict. You have to turn it in the Monday immediately following when it was due. And your pre-labs are due on a Saturday, so there's not much time there to turn in your late work, and then you're working with half of the points to begin with if you turn it in late. So just keep that in mind as you're completing your pre-lab. Your report, your lab reports are due on Wednesdays, so that gives you a few more days, but still you're still only working with half the points. And if it goes beyond that, you're getting 0 points. But if you don't submit any of the labs, you're going to have 5 pre-labs and 5 write-ups. You have 6 labs. The first one is orientation. And I don't believe there's a write-up associated with that one. But the 5, if you miss one of those, you get 0 for your entire lab score. That begins knocking you down 20% of your final point total just off the bat if you don't submit a pre-lab or a lab. Is that clear? Let me make that clear. That's the Dr. Marsland model. He's tough, but he's learned from experience that this is what's necessary. Otherwise, you go, oh, it's only 5% of my grade. I'm not going to do that lab. And we want you to do all of the labs. It's important. The other thing that I did try to do, I'm not sure that I can promise you that I will do this all the time, but I did try to post a partially filled out set of notes. I sent an email last night late after it was completed, so that you could then maybe have that to write on, and you don't have to frantically write everything down if you're one of those that tries to do that in class, which is kind of what I tried to do. But this will maybe save you some time. We talked about the grading. We're going to start today with a game, who has the answers, and then we'll go through and define current, which is the rate of change of charge for a given amount of time, or how many charges, electrons or positive charge. And in ECE, we deal with positive charge. How much positive charge moves past a particular position in a given length of time. And we look at that differentially, so that's now dq dt, where dq is the change in charge, dt is the change in time. Voltage is the change in energy per charge, so that's dw dq. And then we'll relate energy and power, and we'll play a little bit with that and use definitions to solve for charge and energy. And that's essentially applying your calculus. If you now wanted to solve for charge, and charge is related to current, we can now multiply through by dt and integrate both sides, and we can find our charge based on how much current is past that point at a given time. Similarly with energy. First question, and this is appropriate since we're in the monsoon season in Tucson, and apparently if you were anybody at the golf tournament, they had trouble with lightning at one of the most recent golf tournaments, sent several people to the hospital, spectators. So it's an important physical act that occurs, and you want to be careful around lightning. But here's the question. The energy in a lightning bolt is A, B, or C than the energy used to start a car. Is it much less, about the same, or much more? Pick your answer and write it down. The energy in a lightning bolt is blank than the energy used to start a car. So how much energy is in a lightning bolt and how much energy is used to start a car, and you're comparing those. And how do they compare? A, B, or C? Everyone have an answer. Question 2. If you had to pay the power company for the energy in that lightning bolt, how much would you be paying roughly? $1,000, $10,000, $100,000, or $1 million? If you had to pay the power company for the energy in that lightning bolt, how much would you be paying the power company? Everybody have an answer? Pick an answer. Force yourself to make a call. That was not a lightning bolt, but it was appropriate, wasn't it? We won't charge for that. The charge transported in a lightning bolt is much less, about the same, or much more than the charge used to start a car. So the charge that's transferred from the cloud to ground in a lightning bolt is that A, B, or C, the amount of charge used to start your car. Everybody have an answer? Force yourself to make an answer. Even if you're uncomfortable, make an answer. Let's now figure out if we can determine some of the answers to those questions. And how can we do this? Well, let's start by trying to understand lightning a little bit. So now this is going to be a challenge. This depends on drawing. So let's say we have a cloud, and let's say that's full of all these electrons, and then we have the ground. and that's positively charged relative to the cloud, and we have this lightning bolt. What's happening? Well, really there's a charge imbalance. There's a difference or a charge separation that's happening. And if you were sitting there, have you ever been in a charged environment and your hair kind of stands on end? Maybe, maybe not. What is that if the lightning bolt has not yet happened? What would we maybe say is in existence? It's static. Static electricity. If in this environment in Arizona, the dry air, you have more issues with static electricity or static charge than in more humid environments. So this is now dealing with static electricity, which those charges don't like to be separated. They like to get back together. And that's where the sparks fly. And what are some everyday occurrences of static electricity or static? Where do you encounter static or static electricity on a day-to-day basis? Your wife's hair? Okay. We have a bad hair day or a good hair day maybe, depending on the weather or other issues. Here I'm thinking about, does anybody do laundry anymore? Static cling? Is there an app for laundry? Probably. Maybe you do that. Collect my laundry and return it, huh? You just push the app button. But if you have anybody lost socks, where'd that pair of socks go? Oh, it's stuck to the towel or stuck to the sheet, or you pull them apart and you have sparks flying. So every day you have issues with laundry, maybe giving you static. Has anybody seen the warnings at the gas pump? Discharge. If you slide across your car seat, you may be charged up. All right? Then you probably want to touch something metal before you start trying to dispense the gas. Or have you seen the warning that says if you're filling up a gas can, put the can on the ground. Take it out of the car. Don't have it somewhere else. Put it on the ground so that it's in constant contact. That charge, if it does start to build up, it's going to immediately go to ground, and you won't have this separation and the potential for a spark. That's why they want it on the ground if you're filling up an empty can or a can of gas at the gas station. So the gas station. What about the lab? Have you had to wear those constricting straps in the lab? What's that doing? Well, that's trying to take all the charge that you might be gathering or generating by your movement and putting it to ground before you touch something on your bench and destroy it or harm it or damage it in some way so that it's not working. Did you wear your wrist strap? Why? Now you know why. All right, so now you probably want this wrist strap or anti-static and there's a reason for that. You're trying to minimize the amount of charge that you might instantaneously dump into your circuit or into some part that you're handling. So how do we keep track of this charge or flowing charge? current. So now flowing charge is now this, we want to keep track of it and we measure it. And call it current. And again, if I try to sketch this, suppose we had this piece of wire, and in this class we like to deal with positive charge, so let me just say that now we have little positive charges, and we essentially pick a slice through that wire, if that even looks pictorially accurate, and we're counting the charge as it crosses a plane that we've cut in our wire. And what's another way that you can think of this in terms of moving charge? Just, well, here we're saying that I of t, our current, is now each of these charges, the change in charge relative to the change in time, and we like to look at it infinitesimally or in the limit, so that now we're looking at dq dt, where this is now charge with units of Coulomb and time in seconds. And we usually don't say coulombs per second as often as we might say amps for the units of current. So amps is coulombs per second. And as we're counting that, one visual to sort of think about, since we can't really see charge, but you can see cars. If you were on an overpass, you could count the cars that pass underneath you. Speaking of overpasses, what was it? The chicken and the road? Why did the chicken want to cross the road? Is that a joke? Was it? To get to the other side or something? So just recently, I'm driving across the United States, and I'm going towards an overpass, and I'm watching all around me because it's kind of twilight, and I know that there are deer and antelope around, and I don't want to hit them. I see a deer going across the overpass, its head and tail. Smart. It wanted to get across the interstate, and it used the overpass to do it. Anyway, when you think now of charge and current, you're going to be thinking, deer, what? Overpass? Yes, question. So now, in that example, would the cars necessarily be going the same speed? Not necessarily, but we're just worrying more about quantized and saying, okay, there's how many cars per how much time. And that gives us then our flow. Here we're saying we want to measure the flow of charge through our wires, and we're concerned about all these electrons. And it takes a lot of electrons to create 1 coulomb of charge. But that's what we're dealing with, is amps are equal to dq dt. So let's look at some examples. Suppose we now have an automobile, and we're trying to now start that car with using the starter motor. And let's assume now that it takes 500 amps for 2 seconds to get that starter motor, or to drive the starter motor in order to turn the engine to get it to start or crank. If that's the case, how much charge have we pushed in that process. How do we do that? Or how do we find the charge involved that we've moved through that motor? We know this, right? I is equal to dq dt. We want q, so we can just multiply both sides by dt and integrate and find q over the interval of time that we're interested in, 0 to 2. So here, if we do that, we can say, okay, q of t is now this integral from t equals 0 to t equal 2 of 500. That's our I. And we're assuming it's constant over that 2-second interval dt. And how much have we used? Well, we've used or had 1,000 coulombs of charge involved in that transaction of starting our car. And a lot of times we'll just abbreviate that C. What about a lightning bolt? Suppose this lightning bolt, we assume, has a current of 10,000 amperes and that it lasts for 1/10 of a second. What's the charge transferred in that lightning bolt? We can do the exact same process that we just did before. We know I is equal to dq dt. We can solve that for q, and we now say, okay, q is this integral from 0 to 0.1 of 10,000 dt. And now we have 10 to the 4th times 10 to the minus 1, or 1,000 coulombs. We've actually now answered one of our original questions. Question 3 was dealing with the amount of charge associated with a lightning bolt and starting a car. How many? Well, I don't know that you need to volunteer. Maybe you want to tell me what you answered, but that was question 3. The charge transported in a lightning bolt is, we calculated 1,000 coulombs. The charge used to start a car, we calculated to be 1,000 coulombs. So B is the answer. It's about the same. How many answered B? About 1/4 of the class. So now this is, therefore, question 3 is answer B. How do we get energy into the picture? Or how does this charge get separated? How do we separate charge? What's involved in separating charge? When you're walking across the floor and you touch something metal, what caused that charge to be separated and then to be reunited when you touched something? What was involved? Some friction, some energy, right? You had some energy involved to build up that charge separation, and then it was reunited with the spark. So there's energy involved in separating charge. It takes energy to separate charge. And that's what we now call voltage. Voltage is, in fact, the energy needed to separate let me say charge through a conductor. Or the energy needed, you could think of that as the work done to separate that charge, and we define that again as a change in the work over the change in charge. And infinitesimally, looking at that in the limit, we have dW dQ, where the units of energy are joules and our charge is in coulombs, and we typically just refer to that as volts. But volts are joules per coulomb. And what's a joule? That's a unit of energy and or work. How do we think of work? Force times distance. And now that's why I brought this, the apple. What's the gravitational force on a smaller apple? How do I find the gravitational force that this apple is experiencing? I can feel it in my hand. Pardon? Mass of the apple times g. That's the force of this apple. So this apple, if we wanted to worry about its force, is mass of the apple times g. And what's g in MKS units? 9.8 meters per second. So this g, so this is now mass of our apple times 9.8 meters per second That's acceleration of gravity. And we wanted to, I said this was 1 Newton of force. So let's say that's 1 Newton. Now we can back out the mass of that apple in English units. If you go to the store, you say, I don't, 1 Newton. Did you put it on the balance? They charge you by newtons at the counter, don't they? They put it on the, boy, don't go to Sprouts on a Sunday, I tell you, especially the Sunday before school. Maybe it's always that busy, but I'm trying, this apple is expensive in terms of time to collect. Where was I? Oh, trying to figure out the mass of that apple. Suppose we don't like 9.8, that's kind of rough. Let's just do 10. So now we know that the mass of the apple is 0.1 kilograms. Newtons is kilogram meters per second, right? That's the Newton. So now we have 0.1 kilograms, and you're going to have to remember all your dimensional analysis. What's the relationship between kilograms and pound mass? Do you remember? Why do I think it's 2.2 pounds per kilogram? Is that about right? So if you take, well, you can play with milk, you can play milk jugs, 2 liters of water, of soda, to get an idea for what this weighs for you. But now this says that it's about what? The mass of the apple is about 0.22 pounds, or let's say 1/4 of a pound. So if I get 4 of these apples that are small, it might weigh a pound. So the next time you go to the store, you might put 3 apples on the balance or 4 small apples and see if it's a pound. And then you can pull one of those apples out and say, oh, that apple has a force of 1 Newton. Well, that force per coulomb gives us 1 volt. So this apple, together with charge, gives us a volt. That's where I was going with it, but maybe... All right, so now we know, what do we know? We know that voltage is the amount of energy per coulomb. So if I did that 1 Newton through a meter, that would be 1 joule of energy. And how quickly I do that determines power, right? Time rate of change of energy is power. So if I did it quicker, that would be more powerful than doing it slow, but I still have the same amount of energy. All right. So now, what do we have? We now have said that voltage, V of t, is equal to the rate of change, the change in energy per charge. And now we can start playing with voltage and current. We can notice the following. Suppose we now look at the product of V of t and I of t. V of t was dW dq. Current was the flow of charge per time. We have change in charge in common. We can cancel those, and now we have that the product of voltage and current is the time rate of change of energy, or that's now instantaneous power. Instantaneous power can be found for a given element or circuit device by the product of the voltage across that, which gives it the push to move, and the current flowing through. The product of voltage and current now is power, which is this change in energy per time. Let's now look at some more examples. What's the next example? Let's say example 2a, which is the total energy used to start a car. And now what are we talking about, or what are we doing? Did we have energy in any of those equations? What was our voltage relationship? V of t was dW dq. Do we know the change in charge to start a car? Didn't we answer that before? And what's the voltage of a typical battery to start a car? 12. So now we can find the change in energy to start that car. Meaning, now we know that delta W is V of t dq. Where V of t, let's just assume for a car battery, and we now can say that our energy to start that car is 12 volts times, how many coulombs or change in charge did it take? Took us 1,000, didn't it? And volts, units of that are joules per coulomb. So that now we multiply those together, mix the units or clear the units, and we have 12,000 joules to start that car. Now let's figure out what's happening with the lightning bolt. Now that we've done that for a car, can we go to the second example, the B example, 2B, which is the total energy released in a lightning bolt. We know the formula. What we have to do, though, is figure out what V is. And let's just go to yesterday I found a book on lightning. It's in the library as an e-book. You can find it. A lot of information about lightning. That's why I didn't get this done until after 10 o'clock last night. But anyway, let's assume that we now just have a voltage V of 500 capital MV. And you'll need to learn the syntax or the way of abbreviating powers of 10 by the different letters. In this case, M is mega, or 10 to the 6. So this is now 500 times 10 to the 6 volts. That's our voltage. That's the potential between the cloud and the ground. That's the voltage, 500 megavolts. And we know the amount of charge that was transferred in that lightning bolt. That was 1,000. It was the same to start the car. But now what's the energy, total energy, released in that lightning bolt? Delta W is V delta Q. V is this 500 times 10 to the 6th. Delta Q was 1,000. So now we have 500 times 10 to the 9th joules. Or that's now 500 gigajoules. Woo! How does that compare with the total energy to start a car? $500 gigajoules is quite a bit more than 12,000 joules, isn't it? So the total energy in a lightning bolt is quite a bit more than the energy needed to start a car. So there's question 1. Hopefully I'm getting the right letters. I think that was answer C. So it takes a lot more energy, or there's a lot more energy involved in a lightning bolt than to start a car. And what's the take-home message there? They both had the same amount of charge involved. What made the difference? If you're yes. Was it the distance? What was the difference in our formula what was different in our expression for the two quantities? Delta Q was the same, wasn't it? But the voltage, and what's voltage? It's energy per coulomb. So the energy required to move that charge through air is much more difficult than trying to move that charge through wires, hopefully that are fairly clean in your vehicle. That's why you may have to make sure it's not corroded. You want clean. You want this flow of charge to be easy in your car, and that's a conductor, a nice wire. It didn't take much energy to move that charge through that system in your car versus all that energy required to get that lightning bolt to do its energy release. So the take-home message is really that more work is needed to move a fixed quantity or amount of charge. That was the same in both. That was 1,000. More work is needed to move a fixed amount of charge through a high resistance medium. And here we're comparing air, which is very high in resistance, to wires. And that's why it was so much more energy involved in this lightning bolt than in starting our car. If there's that much energy in that lightning bolt, how much is it going to cost us if the power company actually charged us for that amount of energy? 500 gigajoules? Are you kidding me? Doesn't take that much to charge your phone, does it? Thankfully. So let's figure out how much this costs. So how much would you pay? I have no idea which question this is. We've answered question 1. We answered question 3 first, so I think this is question 2. So this is now back to question 2. How much would you pay the power company? Or how much would the power company ask you to pay, whether you paid it or not? You pay your bills, okay? How much would you pay, but you don't have to pay for these lightning bolts, thankfully. How much would you pay the power company for the lightning bolt? And this may be a little bit low, but let's just assume that the power company have an energy cost of 10 cents per kilowatt hour. Have you looked at your power bill? Maybe you don't look at it, but you pay it whether you look at it or not. So let's let the energy, just to give us a clean number, let's let it be 10 cents per kilowatt hour. And what's a kilowatt hour? Well, that's exactly what it says it is. It's the power over 1 hour. 1,000 watts over an hour. And we can now figure out what that represents in a number. So 1 kilowatt hour is 1,000 watts times, and now we need to convert hours to seconds to get that to joules, because kilowatt hours is energy. So this is now the watts. The hours, we know we have 60 minutes in an hour, and we have 60 seconds in a minute. Or we now can say that we have 1,000 times 3,600 watt seconds, which is joules. Joules is, or power, which is watts, is joules per second. So this is now power, a way of thinking of that, that's in watts, is equal to joules per second, so that now this is joules. So we have 3,600 times 1,000, or 1 kilowatt hour is 10 to the third times 36 times 10 to or, I don't know why I'm playing so much with this, but I'm just having fun. 3.6 times 10 to the 6th, or 3.6 megajoules. That's 1 kilowatt hour. And what's it going to cost us? The cost is now, what did we have for that? We could also write this as 0.5 times 10 to the 12th joules, since this giga is 10 to the 9th. So now our energy in that lightning bolt is 0.5 times 10 to the 12th joules times $0.1 divided by 3.6 times 10 to the 6 joules. That's our cost per energy, or dollars per energy. The joules cancel, and we now end up with 0.5 over 3.6 times 10 to the 12th times 10 to the minus 1, there's our dime, times 10 to the minus 6. And that's our dollar amount. And if we really wanted to say, I said roughly, so let's do this rough. Let's just replace that 3.6 with 5. That's pretty close. I said rough. So now we have 0.5 divided by 5 times, and I can do the addition maybe of the factors, the exponents. I now have 10 to the 5th. Yes? 0.5 divided by 5. I can do that, I hope. That's now 10 to the minus 1 times 10 to the 5th. That's now $10,000. Is that right? So that energy bolt, what were we doing? We were trying to figure out how much the power company would charge us if, in fact, we needed to pay for the energy in that lightning bolt. And now we calculated that to be roughly $10,000. And now I can't remember how many lightning bolts hit the earth. It was in that lightning book. I apologize, I don't remember. It's a lot. But it would not be very feasible if you're going, wow, let's do that for our energy budget. We can't really capture that. It happens fast. And what would you have to do? Store it. How do you store anything fast? Batteries are slow to charge, aren't they? That drone, I just flew it for 20 minutes. Now I have to wait a day to fly it again. Charge the batteries. No, you have 2 sets of batteries or 3. But capacitors charge faster, but still. And then how do you find that lightning? Do you pull a Ben Franklin? Fly a kite? Anyway, it's not feasible to try to capture lightning and solve all of our energy problems. We'll pick up with charge and voltage and how we move all of that around tomorrow.